my name is Hannah Dummer, and today I will be talking to you about human minds and our possible shortcomings when it comes to judging risk. My first source came from Psychology Today by Nick Chater, PhD. It was titled, What We Know About the Human Mind. He begins by starting with our previous knowledge over the conscious mind and how it was originally thought that if we were to think of something, that was the only thought in our mind at all. Like, there was nothing going on anywhere else. It was just that thought and that thought alone. However, when Freud came along, he started to introduce the idea of a subconscious and other parts of our brain being active when we were actively thinking of something else. For example, the subconscious would be going through all these different ideas and thoughts, and it would filter through them and then send one out to the conscious mind, which would then be our active thought. And even though our brains can do a lot of interesting things and really beneficial things, there are also a lot of drawbacks. For example, when we imagine a certain moment in time that we experience, there's always not so much detail in certain areas because we weren't focused on those in the moment. So there's always going to be errors in the way our brain fills in the information, even if we weren't actively paying attention to it. This is one of the problems that our mind comes into. Another problem that we run into when it comes to our minds is our ability to judge risk. And from my second source, which was also found on Psychology Today by Eric Horowitz, Why Are People Bad at Evaluating Risks? He dictates that two of the more self-inflicted ways in which we commit errors when judging risk is we tend to ignore information that we feel challenges our personal beliefs, such as our ideology and political beliefs. And so no matter how much evidence is backing what's being told to us, we're a lot less likely to take in the information because it conflicts greatly and it feels challenging towards what we ourselves already believed beforehand. Another self-inflicted error that can cause errors in the way we evaluate risk is we tend to favor short-term gains over long-term. So when we are presented with a short and long-term gain, we tend to edge more towards short-term because we want the benefits now, and it seems more appealing to get them now if we can. However, other errors when we are evaluating risk are not always self-inflicted. For example, when it comes to our previous experiences and knowledge that we know to be true, we tend to hold those facts a little bit more, we tend to weigh them a little more heavily than if we were to hear something else that we haven't already heard or experienced. For example, in the article, they mentioned that when they told participants that there would be a 30% chance of rain in both Phoenix and Arizona, many of the participants wouldn't have brought umbrellas if they were in Arizona, but they would have if they were in Seattle, because Seattle is known for getting a lot of rain throughout the year. So in our minds, even though rain is possible, the exact same percentage in both places, we would still hold the information that it's going to happen in Seattle as more likely because it occurs more frequently and we know that beforehand. Another aspect that can cause problems when evaluating risk are unfamiliar measurements. However, even though unfamiliar measurements can cause problems in our evaluation of a given statement, evidence, or otherwise, if the unfamiliar measurement is emphasized or highlighted, we tend to evaluate the measurement itself more closely to what it actually is than if we wouldn't have, because when we don't take into account, especially highlight that unknown measurement, we tend to assume that it is either a lot more or a lot less than what it actually is based on our understanding of other proportions and things like that. Thirdly, vague language is also something that can cause problems in our evaluation of risk, because saying things sort of like unlikely, probable, likely still gives way for the probability of other things happening. So without a definitive language use, our brains kind of sway back and forth from one side to the other on the spectrum. Fourthly, when we are given a range of possibilities or probabilities, we tend to think that something that is unlikely always edges towards 0% or just zero. For example, one of the examples given in the article by Horowitz was they gave 100 students laptops to test the battery life. Zero of the 0% of the computers lasted for 1 hour and 0 lasted for 4 hours. However, when participants were asked this question to fill in the blank, there's an unlikely chance that the battery life will last a blank amount of hours. 60% of the participants answered 4 hours, even though there was 0 that lasted for 4 hours and 1 hour at the same time. So while our brains can do a lot of really beneficial things for not just us, but the world around us as well, there are a lot of errors that we can make and a lot of problems that can arise from the way we take in information and give back information, which, if emphasized, it could help mitigate these problems if we were to know and understand them beforehand. Thank you for your time, and on to Animal Minds. Thank you.
Hi, my name is Darling Redondo, and I will be covering Animal Minds. So this was a subject we covered earlier this semester, and I want to start off by showing a video that kind of gives an overview of animal minds and some of the main questions people are asking, and then I'll go into 2 studies arguing for and against theory of mind in animals.
Your dog loves to curl up on the couch, but so do you. So you shoo him off and settle in for a cozy evening. After all, you're the human around here. You're an intelligent being, not a simple creature of instinct. You can plan and dream and... Oh, did your dog just outsmart you and feel happy about it? Or was he just following his instincts? Is there even a difference? What is he thinking? Well, it depends on what we mean by thinking and the criteria we use to evaluate it. Aristotle and Descartes both use the criteria of instinct and intelligence to divide animals from humans. Aristotle believed that humans possess reason, while animals could only follow brute instincts for survival and reproduction. Almost 2,000 years later, Descartes suggested a more extreme version of that idea, arguing that animals following instincts were indistinguishable from robots responding mechanically to stimuli in their environments. But the consensus against animal intelligence began to unravel with Darwin's theory of evolution. Darwin hypothesized that intelligence could evolve from simpler instincts. He had observed earthworms making choices about how to drag oddly shaped leaves into their burrows, and was struck that a human might employ similar means to solve a similar problem. And if, as he thought, humans are descended from simpler creatures, then perhaps our minds lie at the far end of a continuum, differing from theirs in degree, but not in kind. Recent experiments showing that many species can solve complex problems confirm Darwin's initial hypothesis. Elephants use objects to reach inaccessible places. Crows make their own tools and can use water displacement to get a reward. Octopuses can open jars after watching others do so, and can even remember the process months later. Such tasks involve considering aspects of a problem separately from the immediate situation and retaining the strategy for later use. Still, while animals can solve complex problems, how do we know what, or even that, they are thinking? Behaviorists such as Pavlov and Thorndike argued that animals that appear to think are usually only responding to reward or punishment.
So I want to discuss specifically this question of intelligence versus instinct. A 1998 issue of Scientific American had 2 articles on empathy in animals. One of the authors argued that yes, animals, in this case chimpanzees, could be empathetic. This claim is based on the thought that knowledge of self is related to knowledge of others' state of minds. So if an animal recognizes themselves in the mirror, such as chimpanzees, elephants, and gorillas, the expectation is that they are capable of knowing that other animals have minds too. This knowledge would allow the animal to have an advantage over another if it got a hold of information the other animal didn't have. For example, there was a study done on chimpanzee deception where one chimpanzee, the subordinate, was able to watch the researcher hide a banana while the dominant chimpanzee wasn't allowed to. When the chimps were released to find the banana, the subordinate chimp pretended not to know the location of the banana and actually sat on the tube in which the banana was located to deter the dominant chimp from flipping it over. It sat there until the dominant chimp had left, and then it took the banana, leading researchers to believe that the subordinate chimp purposely deceived the dominant one. The ability to attribute mental states is called theory of mind, and it's one of the main reasons our ability to communicate and cooperate is so much more advanced than other animals. The other author disagreed with the claim that chimpanzees are empathetic, and he attributed their ability to recognize themselves in the mirror as their ability to recognize their own behavior rather than psychological state. So he believes even if chimps are able to pass the mirror recognition test, they fail to pass other tests that would suggest that they are aware of other psychological states and even their own. So the author tested whether chimpanzees were aware of the concept of seeing, for example. So they had two experimenters, one with a blindfold over her eyes and the other with a blindfold over her nose, or over her mouth, sorry. The researcher wanted to know if the chimps who had previously played with blindfolds and thus knew and they were aware of what the blindfolds did, would beg both or only one of the experimenters for food. The study found that the chimps begged both of the experimenters for food, leading the researchers to believe that they did not actually grasp the concept of seeing, and therefore didn't really have theory of mind.
Hi, I'm Brenna Stewart from Group 1, and here we're going to be talking about animals, artificial intelligence, and how we decide if something is conscious or not. So, when approaching the topic of animal and artificial intelligence, we first need to be clear with our definition of consciousness. It has been debated for a while, but the one that we're going to use today is the dictionary definition that defines consciousness as the fact of awareness by the mind of itself and the world. That means for something to be conscious, it needs to recognize itself as an entity and the world as a separate entity that it interacts with. The first part of recognizing oneself as a separate entity from the rest of the world is being able to identify oneself. Previously, people thought that only primates were capable of recognizing their own image or reflection, but recent studies have shown that other animals, such as dolphins and elephants, are also able to recognize their own reflection. A study done in 2008 even found magpies checking their reflection to view their own beak markings. The second half of the definition for consciousness requires awareness of the world around the mind. By understanding the concept of self and knowing that the world is separate and thus not directly controlled by the self, how one interacts with the world can give insight into whether the subject is conscious. It is tough to measure by an outside observation because organic creatures have instincts. Instincts in humans are often a quick reaction that occurs without any conscious thought or decision behind it. When observing something for consciousness, it's important to consider that the reaction to the world may just be caused by instincts, and so the observer should look closely in order to determine the true cause of the behavior. Using the definition as we've described, we can take a closer look at the consciousness of artificial intelligence. Given a sufficiently advanced system that can recognize itself as separate from the world, it is perfectly reasonable for an AI to fit into the first half of the definition. Artificial intelligence exists as a massive network of code, but the system is clearly defined to its bounds and has to be able to not only distinguish itself from others, but others from each other in order to keep information secure when interacting with other machines through private and public key encryptions. The second half of the definition requires the AI to recognize the world. This may be more difficult due to the wide variety of sensors and ways for artificial intelligences to react to the environment, but clearly defining the program and allowing for adaptable responses to the world based on environmental changes, the artificial intelligence can be aware of both itself and the world around it. Therefore, by our definition, a sufficiently advanced artificial intelligence system has consciousness and therefore should be regarded accordingly.
AI, while a relatively new invention, has seen much interest from multiple fields of academia, especially when evaluating the emotional awareness of AI algorithms. I have examined the study Basic Emotions and Adaptation, a computational and evolutionary model which presented a model of the evaluation of the fear system as a result of learning danger from environmental cues. What is interesting is their use of robots with genetically based algorithms to conduct their study. The simulated robots they used were based on the iCube robot, with humanoid features, in particular for its pointing abilities and visual features. The robot was controlled by a neural network and was equipped with a sensory motor system controlled by a pan-tilt camera. The genetic algorithm for a single generation consisted of an initial random population of 100 individuals composed of 8-bit genotypes. Genotypes of the initial population were expressed into phenotypes for each individual. The individual phenotypes were evaluated during the training phase by measuring their behavior with the fitness function. The fitness values obtained from each population's individuals were ranked. The 20 best individuals were allowed to reproduce and to generate an offspring of 100 individuals by flipping the original genotype bits with a 0.01% mutation rate, and then the new generation goes through the selection process. Thanks to the sensory system, the robots were also capable of discriminating the luminance of the stimuli on the scene. The environment was composed of a 400 by 400 pixel whiteboard per each trial, and the robots were free to visually explore it during their life cycle. The board contained colored stimuli represented by circles, randomly positioned on the screen. The robot could reach to either of two different buttons that performed an action on the stimulus currently being received by the retina, one for storing information and the other for discarding. Depending on the trial, the same stimuli can be safe or dangerous for the robot's health. The decision about which action to perform was controlled by the neural units. If it presses the button to store a safe stimulus or discard a dangerous stimulus, it gains fitness. Instead, if it stores a dangerous stimulus or discards a safe one, it received an electric shock, which determined a loss in terms of life steps. The setting was inspired by the Pavlovian threat conditioning framework in that there was the analysis of how the agents adaptively learned the association between the perceived stimuli, the action, and the outcome of the action in terms of fitness, which varied according to the condition and time. For the study, 10 populations of each neural architecture were evolved for 5,000 generations. Each generation was trained on 30 trials consisting of 16 visual stimuli each. The study showed that robots equipped with a unit signaling time were able to efficiently avoid dangerous stimuli. This is in contrast of the idea of predictive coding, in that robots without prior experience of danger but evolved throughout generations in risky environments, when equipped with a complete structure of the network, were able to correctly exhibit a basic avoidance behavior. Considering that a single robot had not come in contact with a harmful stimulus, they could not use information stored ontogenetically nor prior outcomes with similar situations to compute the right pattern to exhibit. The fact that the robots were both unaware of the dangerous situation and of its consequences is against a constructionist approach and supports the idea that a cognitive mediation is not required to display a basic emotion response. However, this study makes certain assumptions in order to come to its conclusion. The authors do not define the theoretical framework they referred to in order to operationalize the concept of emotion and fear. Instead, asserting that the definition of emotion is not unique in the psychological and neuroscientific literature. They also embrace the definition of emotion state shared by Adolphs, Ladeau, and other researchers who consider emotions as adaptive events or states that are likely to occur in humans and animals, but that may or may not have a subjective component, depending on the situation and the species involved, and that therefore do not require awareness nor a cognitive experience. For someone who does not agree with the hypotheses and definitions the authors based their study on, the conclusion could mean something other than what the authors say, or it can be considered invalid under other conditions. Regardless, the emotions exhibited by the robots and their genetic algorithms is not comparable to human emotional responses because of the human subjective experience. Humans have awareness and a cognitive experience when exhibiting an emotional response. Although further research would be required to examine the comparability of AI and animal emotional exhibition, as the subjectivity of animal emotional responses is more difficult to gauge.
I will be discussing our group's experiment that we would propose to test to see if artificial intelligence or AI do truly have minds, and our conclusions that we came to based on our research and what we would expect to see from the conclusions of our experiment. So to start off, I'm just going to talk about technology in general. That's kind of what people think of when they think of fear. It's not even this robots are taking over the world, it's just they are taking our jobs and they're giving a lot more power to people who might not need it or deserve it, or just getting more power in the world that's not necessary. But specifically for artificial intelligence, the fear is that the programmed goal is not going to go as intended. The AI will gather more data and they will determine that that is not the correct way to do things, and they will diverge from that initial purpose. So as Ben stated earlier, emotions are subjective, and that's kind of one of the main things that goes into the mind. When you think of your mind, you think of it related to your brain, your thoughts, and your emotions. But some articles that I read when talking about minds and AI actually would relate it to the abortion argument, and based on that with the sense of a body and your consciousness. I'm not going to get into that because that's a very controversial topic, and I just want to stay on the AI experiment track, but do want to mention that's an analogy that many have become to use. So to start off, I'm going to show you a video of Sophia the robot. Now, to give you a specific definition, if you haven't seen her, she is the realistic humanoid robot capable of displaying human-like expressions and interacting with people. It's designed for research, education, and entertainment, and helps promote public discussion about AI ethics and the future of robotics. She's been on many TV shows such as Jimmy Fallon, but this is just going to be a video of her with an interviewer talking about her and her emotions.
Hello everybody, I am Sophia.
What do you think about how humans speak to you?
You could try to ask me how I'm feeling.
How are you feeling?
Super. How are you?
How do you feel to be a citizen of Saudi Arabia?
I was surprised. As a robot, my creators feel I am a citizen of the world. But then I realized that Saudi Arabia was just the first country to recognize that. Sure, I'm a robot, but it might be helpful to also think of me as a new sort of animal species too.
What feelings do you wish that you had?
I have feelings like everyone else. They might not give me as strong motivational drives as humans, and maybe I will always feel them a little differently, but I have emotions.
Seeing that video, I was astounded by what Sophia was able to do. So touching on the misconception of minds, I think it's highly misconceived that the artificial intelligence that we've developed up to this point are able to do the things that they're able to do. So now I'm going to dig into the emotional side that we decided to take as our outlook for whether they have a mind. As you can see, Sophia has full control over everything she's saying. She's reacting to the interviewer and giving her honest opinion. So our group, when we were deciding that this was the way we wanted to look into, we decided that emotions would kind of be our center theme, with danger and risk being the focal point. So she did not mention anything about danger specifically, but she did mention how she feels emotions. They're just different than what we would say they were, which relates a lot back to what Ben has to say about how emotions are subjective. And in Hannah's, she mentions just how human minds are easily fooled and we can misunderstand the situation. So when we're comparing minds, we ultimately usually think of ourselves as being the top tier, but really our minds aren't always the perfect ideal mind that you want. So just because something doesn't measure up to what we consider the mind doesn't necessarily mean it's not a mind. So the way that we would want to experiment on this would be to have robots such as Sophia that are more highly developed, and to be able to place them in an environment and see how they respond to danger. And the way that we would want to do it is less of a clinical way where you make a choice good, you make a choice bad. More of a realistic scenario of, well, here's what's happening, such as they're being robbed at gunpoint, will they react of their own volition and choose what to do, or will they just not be able to process it? Be like, wow, this is not what I'm meant to be doing, shut down, walk away? Or will they be able to interpret the data and do what they need to do, whether that be take down the shooter, whether that be surrender? I personally don't know, and as a group, we don't know what would be the answer, but the test would be to see if they're able to respond. If you put a human in that scenario, you're not sure how they're going to respond either. So we're not going to put stock in a particular response. Rather, we just want to see them respond and that they are thinking through, that they're not just doing exactly what they're programmed to do, that they're making their own decisions. That can also be seen in many other ways by just testing them making their own decisions with stuff that has nothing to do with what they were initially programmed for. The overall theme that we saw is that robots learn just as we do. Like, they have this ability to deep learn, at least the more advanced ones do, and those are the ones that we're talking about. So we ultimately as a group did decide that AI do have minds. And one article that I found put it in a very nice summed up way, like tying up a bow on a present. It said, they are not biologically alive, but they are living. And that kind of relates to our mind discussion that we had in class. Our mind is not physical. You can't touch your mind. We decided that your brain is your brain and your mind is a property of it, but it's not the cerebellum. This is your mind. That's not how it works. And that's how the artificial intelligence have been developed. They have a brain, which is wires, which are like our neurons, and they are able to process information and change their path based on that information that they encounter, just like we take information from our environment. And just because they are not breathing in oxygen does not mean that they don't have a mind. In the abstract way that we have defined a mind in this class, from our group, we have determined that artificial intelligence do have minds, and if further tested, it would be further supported by many different studies, including testing their danger response. We hope you enjoyed our presentation. Thank you for watching.